Hi, this is MEC 3820 Heat Transfer, so Lecture 2 for the Summer 2020 course. So what we're going to do today is we're going to discuss the different modes of heat transfer. So we are going to look at, as we mentioned at the last slide, we're going to look at conduction, convection, and radiation. So first we need to discuss exactly what we mean by heat transfer. So in this case, why don't we just consider a system that has two masses. The two masses are identical to each other in terms of their material. The only difference between them is their temperature. So cube 1 has a temperature of 100 degrees C and T2 has a temperature of 50 degrees C. So they have different energy levels. So if we are going to say at time t equals 0, we begin to observe this system, and once we let time progress, what does the second law of thermodynamics have to say about this situation? So since we're not in an actual classroom, you're going to have to think about that yourself, and we'll move on to the next slide. So now we can have three different cases. So we can put those blocks together such that one of their sides are touching in direct contact, and then we can put perfect, right? I'm going to put quotes around that. Perfect insulation around these blocks. Perfect insulation means that you can think of the insulation layer as being infinitely thick, but what we really want to do is say that that insulation is so good that it lets no energy transfer into it. So this is again something like unobtainium, right? There's no such thing as perfect insulation, but we can use it in a thought experiment. Now the other type is that we can have the blocks surrounded in an enclosure made of a perfect insulator, and the enclosure is maintained at a perfect vacuum. All right, so we have that situation. And then the last one is the situation is much the same as the second one, except that we have a partial barrier so that block 1 can't see block 2, and then we fill the volume with some type of gas. All right, so those are going to be our three variations of it. We're going to refer to this one as heat transfer through conduction. This one is going to be heat transfer through radiation, and this is going to be heat transfer through convection. So what we're going to do here is let each case will begin at time t equals 0. So nothing's changed. All we've done is we've taken one of the blocks is 100 degrees C, the other is 50 degrees C. The blocks are made of the same material, the blocks are the same size, and the only thing that's different is the relative position and the system that they're contained within. So once we set the timer, we will then let time continue, and as we observe each case, we will find that after some finite interval of time, each system will reach a steady state such that T1 equals T2 equals 75 degrees. So what this basically means is that there was an imbalance in energy within the system, and then the second law says that, right, the second law is the law of entropy, which basically says that energy will try to reach its lowest value, right? Entropy has to increase. So having one portion of the system at a higher energy level than the other is at a higher entropy level than you let all that energy essentially lay out, right? Become level across the entire system. But what we do note in this theoretical experiment is that the time it takes for the conduction case to reach equilibrium is not the same as the time for radiation and not the same time for convection. We're not saying that any of these are greater or less than each other. We're just noting that they take a different amount of time. So what we're going to conclude from this is that the rate of heat transfer, what do I mean by the rate of heat transfer? Well, heat is energy, that's joules. The rate of heat transfer is the amount of heat energy that's transferred per unit time, so joules per second, which is going to be watts, right? In the SI system, joules per second is the units of power. So the rate of heat transfer really talks about the amount of power that's being transferred. And we're going to write this as Q. Little q is going to be our unit for the rate of heat transfer, which has the units of power, and it's going to be the change in thermal energy of a system over the time that it takes this certain amount of energy to change. So it's going to be like 500 joules per second, right? And the units are joules per second, so we'll refer to that as watts. So for conduction, we will, to give it the definition, conduction is the rate at which heat transfers through a solid material. So if we have a slab of material that has its two phases maintained at two different temperatures, so the surface area, now again what we're looking at is we're looking at a side view. The slab is in and out of the paper, so this side is at a temperature of 30 degrees and this side is at a temperature of 0 degrees. Now what we're going to do is, and these I and O, it's not initial and final. The TI, so we'll refer to in conduction that there's an inner surface and an outer surface. So in this case, we have the length of the slab, or right L, but we really usually refer to it as thickness, even though instead of using the letter T for thickness, we consider L, right? L is our length parameter. So we're going to say that the thermal energy transfers through the slab at a rate defined as Q. And again, according to Newton, the second law of thermodynamics is that the direction of heat transfers from high to low, right? We have a high energy state and a low energy state, and the energy is going to transfer in that direction. So what we define as a heat flux now, so we have a heat rate Q, but if we have to have a set surface area, then we can divide the heat rates by area, and we will get what's referred to as a unit, as an energy flux, or an heat flux, right? It's not energy now, it's power. So this will be watts per square meter. So and a lot of times we'll be looking at, say we're looking at a big wall of something, and we're not really concerned about 1 square meter of the wall, but we want to know is for a wall that's say 35 square meters or 100 square meters or 1,000 square meters, what is the heat flux? Because if I know the heat flux, in other words the amount of energy transferred per unit meter, well then I can just multiply by the number of meters that I have. So that's why we mostly in conduction will be dealing with a heat flux, or at least when we're dealing with what we were going to refer to as a flat wall. So now we've defined what conduction is, and now we have these smart guys, way from the past. This guy's Fourier, and Fourier came up with the law of conduction. So this was done empirically, which means he did experiments, and what he observed was that the heat rate was proportional to the area. So if you double the area, you double the heat rate. He also found that if you double the temperature difference, you double the heat rate. And he found that if you doubled the temperature, or doubled the length, the width of the wall, you would have the rate of heat transfer. So these are all linear dependencies. And what he did find after doing a bunch of experiments was that these relationships would always hold, but they would be different for different materials. So this proportionality constant that comes up is a material property, and that material property is known as the thermal conductivity and is defined by a symbol K. So the Fourier's law, written as a heat rate, is Q equals K times the area times delta T over L. If we wanted to write this as a heat flux, so Q double prime, it would be Q double prime equals Q divided by A equals K delta T over L. Okay, so I'll leave it for you to determine what the units of K are. All right, so the units of K are what makes this proportionality constant work. So I'll leave that up to you. So now convection is the rate at which we can transfer heat from a solid surface into a gas that's flowing over it. So, well, you technically don't need the gas to be moving. You can have what's referred to as free convection. When we're talking about a moving fluid, we're referring to forced convection. And that's primarily what we're going to be dealing with right now. So consider this interface. We have a solid surface here at some temperature, and then we have a gas flowing over it. We'll typically look at gas flowing parallel over to the surface. So this is going to be, again, going back to your fluid mechanics, your classic flat plate. So we have a flat plate, we have fluid flowing over it, and what we'll say is that the fluid moving over it will be at a constant temperature, T infinity. The free stream temperature. And what we're going to note is that energy, right, a flux in this case, because we'll be given some sort of area, but we will typically want to know how many watts per square meter is being transferred. And the heat rate can either, or the heat flux can either go out, so from the surface into the fluid, or from the fluid into the surface. Again, when we're referring fluid, this can be gas, these can be liquid, so we can be dealing with any type of liquid, or fluid rather, that's flowing over the surface. All right, so just stating it officially here, or in words, so if TS is the temperature of the surface, is greater than T infinity, the direction of heat transfer will be from the solid surface into the fluid. And if the free stream temperature out here is greater than the surface temperature of the solid, then we will have transfer into the surface. And the law that relates this is referred to as Newton's law of cooling. So in this case, again, it's an empirical observation where the rate of heat transfer is proportional to the area. Double the area, you double the rate of heat transfer, and if proportional to the delta T. So if you double the temperature difference between the surface and the fluid, you will double the rate of heat transfer. All right, so again, we find out that if we take a look at different values, we find out that in this case, the material property, the material doesn't matter, right? So we have a certain material, and we find out that we're getting the same type of heat transfer. But what we do find is that there is a more complicated relationship between the type of gas that's flowing and the speed at which it's flowing, and a bunch of other little parameters that is going to form the basis of the second portion of this class, i.e. convection. But in this case, and for the first couple weeks, or the abbreviated number of weeks here, we will be dealing with this, and we'll just call it the heat transfer coefficient. Okay, so what are the units of H? And so figure that out, and I say, can this be expressed as a heat flux? Well, of course it can, because we have area on this side, so I can divide both the left-hand side and the right-hand side by area, making this a heat flux. So the third and final form of heat transfer is referred to as radiation. So this is the rate at which heat transfers between solid objects. We can have gas as well, but for our purposes, we're going to assume that everything is a solid, and it's due to the emission and absorption of electromagnetic radiation. So you say, whoa, wait a minute, we were dealing with internal energy, translational, vibrational, rotational. You were comfortable with that. So what is this electromagnetic radiation? Well, again, from Physics 3, you should have some idea about this, but you know that all objects can radiate heat, and that heat can be emitted both, or transferred, right, by conduction and convection, but also by radiation, because the heat coming off is an electromagnetic wave in the infrared spectrum. So we have visible spectrum, we have the infrared spectrum, we have the ultraviolet spectrum. So when we're talking about the heat given off by a solid object, that the wavelength of that electromagnetic radiation is what we refer to as infrared radiation. So in this case, we will have a temperature of the surface of the object. So we might have a small object within a very large enclosure, and in this case, we have the temperature of the surface, and then we have the temperature of the wall of the enclosure. A lot of times we would just refer to it as the surroundings, right? Because you can have something out in the middle of interstellar space, and that object would have a surface temperature, and then the infinity of the vacuum around it would be the temperature of the surroundings. So if the temperature of the surface is greater than that of the surroundings, you'll have a net rate of heat transfer going from the surface to the surroundings, and vice versa. If the temperature of the surroundings is greater than the temperature of the surface, you'll have a net radiation going towards it. What do I mean by net? Well, the surfaces are constantly giving off infrared radiation and absorbing infrared radiation, and it's the imbalance in those, right? If it's absorbing more than it is emitting, well, then it has a Q net coming into it, and if it is emitting more than it's receiving, well, then it has a Q net leaving its surface, or leaving the body itself. All right, so funny enough that the radiation heat transfer doesn't have anybody's name associated with it, but there is a quick empirical formula that we can use. So again, through observations, we find out that the rate of heat transfer is proportional to the area, but now not proportional to a delta T, right? It's proportional to each of the temperatures raised to the fourth power, and you're subtracting them. So you take your surface temperature, raise it to the fourth, minus the surrounding temperature raised to the fourth. So now I have down here, does it matter if the temperatures are given in delta C or centigrade or Kelvin? Well, you can answer this question for yourself, and I'll let you say that this is 100 degrees and say this is 50 degrees. Well, the delta T is going to be 50 degrees, but it's not. So now you would have to raise 100 to the fourth and subtract from it 50 to the fourth. Well, now if you raise 373 to the fourth and subtract off from that 323 to the fourth, see what you get. All right, so we do some experimental observations and we find out that there is a proportionality constant that is not dependent on any of the physical properties. This is known as the Stefan-Boltzmann constant. And then there's this E, written as the Greek letter epsilon, and this is referred to as the emissivity of an object, surface emissivity. So there's a lot more complicated stuff going on here. So we will not be dealing with the radiative heat transfer until we get to that section of the course, which will take place in the last 2 weeks, week and a half of the semester.